I wanted to congratulate the 3 founders of this program who actually did more than found this program. As far as I'm concerned, they had a big influence on my career by creating opportunities for me that really wouldn't have been available otherwise. I'm going to talk about my own experiences, which don't necessarily represent all of chemistry, but I'll say a little bit about that in a moment. So I came here because of this program in 1963, and didn't actually move into this building until between 63 and 64. And I occupied a large, significant fraction of the 3rd floor, right next to Eli Burstein. And my interaction with physics was made obvious by this first picture that I have. So I persuaded Eli Burstein to accept this paper, which was the first use of an ultra-high, which then 110 kilogauss, or 10 Tesla you would call it these days, magnetic fields on molecular systems was new and exciting, and that's what we did. But one of the amazing things about this program, which I suppose is underlying everybody's comments, was the immense support that we got. We got support of people. We got support to buy equipment. We got support to use resources, to use facilities, to use machine shops. And it was possible for me to move ahead in a variety of different areas that it really would not have been possible elsewhere for me to do. So during that time, of course, things were very formative here. And the way the program is now looks extraordinary to me. I've not been part of this program for a significant number of years. Excuse me. But as it was forming, the program was, as I said, it was giving people the opportunity to change direction. I heard somebody else mention the same point. I think this was what was exciting for me. At one stage on the 3rd floor, I had archaic photographic spectroscopy going on one corridor, and building one of the first picosecond laser systems on the other side of the corridor. And things were moving very quickly. I was changing fields very quickly, and largely becoming more and more interested in biophysics, which really is what has occupied me, since I've been gone from this program for just some time. So chemistry was important, but it was a lot of work to make chemistry important. So one of the most outstanding contributions, outcomes of this program was the Nobel Prize to Alan Heeger and Alan McDermott. In the early days of this program, when I was sitting, I think maybe with Charlie Eden on the executive committee, I fought very hard to try to get physicists to incorporate synthetic chemists into the program. And gradually came about a strong interaction between McDermott and Heeger, and the exciting result of all of that, which was a Nobel Prize. And, I think that really says something very, very important for this program, that it managed to bring this together. So things went on, and I became less interested in photographic spectroscopy and more interested in ultrafast phenomena, and that's basically what I've been doing since then. And I thought, since I was kindly put on this program, I'm actually just going to introduce the 2 following speakers who are ex-members of my research group from very different areas. And there are many people in this audience, much to my delight, who shared experience with me on the 3rd floor of this building and also in the chemistry building. So thank them all for coming. I greatly appreciate it. So I thought, though, nevertheless, I would just say a little bit about what I do now. I'm sort of living proof of the fact that you can be successful without this program, actually, at this stage. Indeed. So I'll say a little bit about what I do, but I just wanted to make it clear at the beginning that I wouldn't be in this situation without the initial stimulus that I got 47 years ago from this program. So what we were interested in, to encapsulate it, really from the beginning was to try to make molecular movies, if you like, to try to be able to make snapshots of dynamic behavior of complex systems. And most of the systems that I'm interested in now are biological systems, mostly with collaborations with people, not in physics or materials, but in a medical school here and in other medical schools. So with this idea in mind, let me just say a few minutes of some stuff that we've done recently. And I've made up one little picture of the context of, do I have to speak into this thing? Of the context of this, and I noticed that Phil Enfinrud, who was a postdoc here some years ago, is sitting in the audience, and just quite by coincidence, I happen to have a picture from his research on one of the things I'm going to show you. So, with that, let me say a little bit about what I do. Maybe I will, anyway. So, the idea, as I said, is to take snapshots of structures that are undergoing changes, and we've always tried to think about doing that. I would say that we've not done it, but many of us just continue, especially Phil, this dream of making molecular movies, which will come about. And my approach is a little bit different. There are, people do NMR spectroscopy, which is actually quite slow. You can't really make molecular movies, but it can watch pieces of structures just being disordered. Or pulsed X-rays from free electron lasers can look at perhaps scattering from single particles and pick up one single diffraction pattern from single pulses. Or one can do time-resolved X-ray diffraction, as has been done by Phil, where you can watch molecules in crystals like carbon monoxide move following short optical initiation pulses. So my approach for the last 7 or 8 years has been different, but has proven to be quite exciting. So what we really want to be able to do is to take the shortest possible snapshots where you can actually look at three-dimensional structure. So my approach is not to use X-rays, but to use what we call two-dimensional spectroscopy, which is the optimized type of nonlinear spectroscopy. And as I mentioned, my interest in nonlinear spectroscopy started here back in the 1970s. And the idea here is to do completely coherent delay spectroscopy. That is, with knowing all the coherencies at all times. If you do this, the spectroscopy picks up all the interactions between the various pieces of the structure where you can induce oscillating dipoles. So you can pull out of the spectra pictures of coupling constants and directions. And if you have enough of these, which is in some range of tens or hundreds, then you can put that back together again with conventional fitting methods to find three-dimensional structures, just as is done in NMR. So that's the idea of this spectroscopy, and it works beautifully. And my lab is basically set up to do this in a variety of different ways now. And we've been able to look, of course, at simple molecule dynamics. You can look at equilibrium dynamics really for the first time. You can't see these changes with conventional methods. These are exchanging structures on a time scale of about 2 picoseconds, which is done with the shortest possible femtosecond pulses you can find. The time scale is limited here just by the time it takes to make the measurement to be able to resolve the peaks that you're interested in putting together to get structures. So recently we've been able to, for the first time, determine a complete crystal structure of a protein, a three-dimensional structure of a transmembrane protein, which has 2 helices in it, where we've been able experimentally to determine the coupling between different pieces of this helix with different pieces of this helix with enough points to be able to recreate the structure using modified Explorer techniques that have been developed by people at NMR. So just within the last month, just to keep you up to date, we've been able to look at the motion of a kinked helix that we can trigger to be unkinked and watch the 2-dimensional spectrum. And this, of course, has to be analyzed by relatively complex back transformations to watching this helix becoming a fully formed helix after about 1 nanosecond of time. So this is what I do. And whoops, we don't need to do that yet. Well, we've done it. So this is what I do. And so I'm right now the director of what the NIH calls a BTRC, Biotechnology Resource, which is housed in the chemistry department. And anyone who's interested in doing ultra-fast structural measurements and has an interesting question or problem to talk to us about, please come over. We'd love to see you. Martin, we'd love to see you.